Hi guys, this is Mrs. Gastler, and in this video we're going to talk about problem solving with Newton's laws. So to begin with, now we'll do this. Okay, I'm going to give you some pro tips, and these are some things that I generally follow. First, I always draw a picture or a diagram of what's going on in the situation because it helps me visualize what's happening, and it also helps me think about what pieces of information are going to be important in figuring out what is going on and what I need to make sure that I talk about or use in equations, and thinking about what's going to affect the outcome and what I need to know. And then when I draw my diagrams, and there's a ramp in my picture, I always make sure I draw a comically small angle on the ramp. So even if it looks like this, I'm going to draw it like this because that helps me figure out where my angle is when I'm finding the components of things. That helps me get the angles right all the time and figuring out what's going on. Okay. Whenever I'm done with that, the next thing I usually do is draw a free body diagram. Sometimes I might skip that and wait for it to come later. A lot of times in AP questions, you're going to be asked to draw a free body diagram and to label the forces, so this is probably going to be asked of you anyway. Sometimes you'll do it anyway if it's not being asked of you because it's useful in finding the net force. Choosing an XY coordinates system is going to be helpful. Always put one of those in the direction of motion of the object. If it's moving, or if it's not moving the way it would be moving would be helpful. If you've got something hanging by ropes, one of these coordinates ought to be along one of the ropes. That's usually helpful in splitting up your attention into its components as well, so that those are along the ropes too. That's always useful in solving problems, making it a little bit easier on you. And then the next thing I often do, and sometimes I do these last three out of order, is to apply all three laws. Sometimes I don't apply the third one, especially if I've only got one object, because if there's not two objects, then I don't really have to worry about the other one. But the first one is necessary, and the second one is almost always necessary. The first one is really helpful. If the net force is 0, I need to make sure that I say so. I'm going to kind of circle this here. If the net force is 0 and you don't say that the net force is 0, like you don't literally write F net equals 0 or F net X equals 0 or F net Y equals 0, you probably lost a point. Okay. Because that's, if it's true and you don't write it down, or if it's true, it's probably worth a point. On any question, if the net force is 0, saying that the net force is 0 is probably going to get you a point on a question in the AP test. Okay. Even if it's just the X or the Y side, you saying that the net force in the X direction or the net force in the Y direction is 0 is going to get you a point as well. Okay. Sometimes you're going to be looking at the system as a whole, and sometimes you're going to be looking at it as a piece, and it really depends on the situation. And then you want to make sure that you're following directions. Sometimes it will tell you to look at the system as a whole, and sometimes it will tell you to look at the system as a piece. And sometimes it will tell you exactly what it wants to do, and you got to make sure you answer the question. Okay. Because if you don't answer the question, you definitely don't get any points. So I have a couple of examples, and they're already answered, and so I'm going to work to keep the answered part covered up, and then it gradually show you what it looks like. Okay. All right. So here's a question. Okay. Example 1, let's turn this over there. Example 1 says the ramp is frictionless, and if the blocks are released from rest, which way does the 10 kilogram block slide, and what is the magnitude of the acceleration? So we got to look at the picture here, and I've drawn on it just a little bit. I've added my coordinate system. There we go. Okay. There. Okay. Oops. Okay, so here we've got our ramp. It has a 40-degree angle. It's got a 10 kilogram block here and a 5 kilogram block here. Okay. I put my coordinate system along the ramp, and then I drew it bending around here because all the pulley does is change the direction, and then my Y direction is perpendicular to the ramp. And then I wrote up here that we're going to look at it as a system as a whole and just at the 10 kilogram block, but it turns out that just looking at the 10 kilogram block is not very useful. So that one is a dead end. Now I redrew the diagram with a comically small ramp because it helps me split things up into components. And that's what I need to do in order to work with my system. Okay, now let's flip this over so we can kind of see what I'm doing here. Okay, so I drew it comically small. All right, so I'm going to draw some free body diagrams here. Okay, so for the net force on the 10 kilogram block, I've got my normal force and tension from the string, and then gravity pulling it down, and then I drew on here the components perpendicular to the ramp and parallel to the ramp, and then it was really easy to see where that 40 degree angle goes. And then over here on the 5 kilogram block, I drew the down, what do we call this, gravity, and I labeled it FG5, and I labeled this one FG10 just so that I could know the difference between those. And then that force is tension, and the tension in these blocks is the same. So this is me applying the third law right here. The tension is in the blocks is the same, so I drew an arrow and I labeled those as equal so that I wouldn't forget. Okay, so I've already applied the third law right there, which is kind of what I'm doing anyway, except I'm only on the free body diagram label. Okay. So I've drawn a free body diagram. I've got an XY system. So I'm applying 3 laws. Okay. So what I can read from the question, once it's released from rest, which way does a 10 kilogram block slide? Well, that's kind of telling me that there probably is a net force. So according to the first law, if it's at rest, it stays at rest. If it's in motion, it stays in motion. But it's telling me that it's probably not going to stay in motion. So there probably is a net force. So according to Newton's first law, I need to figure out what the net force is, and then Newton's second law will help me figure out what the magnitude of the acceleration is. So I need to find the net force, and then I need to find the magnitude of that acceleration. So that's me applying the what do you call it? The second and or the first and second law. And I already applied the third law with the tension right there. Okay. So if I do what I know, okay, if the net force is 0, say so. So the net force in the y direction is definitely 0. This block is not going up or down. There's no acceleration off or into the ramp there, so I wrote that one. And that lets me know that the FG10 in the y direction, this force right here, and the normal force are the same, so I wrote that down. What I really need to know is the F net in the x direction. Okay, now on this side, I'm going to quickly reach the end here, because FG10 in the x direction minus the tension is going to give me the net force in the x direction, but I don't have a clue what the tension is. Okay, I really don't know, and I can't know because I can't get it from this other block right here because I don't know how those relate, because I don't know what the acceleration is, so I can't write down any kind of formulas there. So this is a dead end, and I'm stuck. So going with just a 10 kilogram block was a bad idea. Okay, and so I'm glad I actually was doing both at the same time. So looking at the whole system actually was the way to go. Okay, so when I write down this formula over here, it looks a little bit trickier. I already crossed these out, so pretend that's not there. So I started, and I went this way first. So apparently the positive x direction is over here, because I started with FG10x, which is pointed that way. And it doesn't have a negative sign on it, so I don't have it being in the other direction. So I subtracted the tension, which is right here, and then I added the tension, which is right here, and then I subtracted FG5, which is going down right there. Okay, and so that's my net x direction. Here I didn't know the tension, and here it doesn't matter because they cancel out. And so I wrote it there with that one. And then I did some plugging in of stuff, M10 G sine theta, which is that side right there. That's the opposite, so it's sine. And then I've got F net x. And then I plugged in some numbers. It gave me an answer, which is a positive number, 14.27. And that tells me that it's going down the ramp. So it is going that way. So the 50 wasn't bigger, so it is going in the direction of FG10x. Okay, and then I used Newton's second law. A equals F net over M. I divided by 15 kilograms, which is the total mass. And there I got the acceleration of the entire system. Okay, and so that is my answer to example 1. Let's take a look at example 2, which I've also already done. Zach, who has a mass of 80 kilograms, is in an elevator descending at 10 meters per second squared. It takes 3 seconds to stop at the first floor, and the question wants to know about his apparent weight, which I wrote down right here what apparent weight is. Apparent weight is the weight that you feel due to a surface that is accelerating. Here we have, it wants to know what his apparent weight is before the elevator starts braking and what his apparent weight while the elevator is braking. And so I wrote a note here. Before means he's going at a constant speed because it says he's just descending at 10 meters per second. And so I drew a little picture up here. This is a person going in a carnival ride in one of those. It's a big circular thing, and it spins really fast, and then it drops the floor out from underneath you. And you have some apparent weight relative to the floor. In fact, if you close your eyes and, forgot what you were doing, you might think you were laying down on the floor. That's like apparent weight right there. Okay. Let me turn this back over. Okay. So let's do some problem solving. So the first thing, we're going to draw some pictures. Okay, so for part A, he's going at a constant speed. That means that his acceleration is 0. He's going at 10 meters per second squared, and there's the elevator going down. See, I drew some whooshies there to show he's going down. For part B, though, he's slowing down. So I wrote that. He's slowing down. He was going fast. Now he's going 0. It took 3 seconds to happen, 10 to 0. And I wrote that the acceleration was directed upward because it's slowing down. So it would be speeding up if it were going downward. So the acceleration is directed the opposite direction of the motion. So it's upward. Okay. I don't have any ramps, so there's no comically small angles. Drawing free body diagrams. I just have one direction here, so I didn't draw a coordinate system either. So I've got FG down and FN up. I'm actually applying a third law here, and I drew them the same way because since the acceleration is 0, the net force is 0. So I just wrote that. And then down here, since I know that the acceleration is upward, I know that there has to be a net force upward, so I drew the normal force bigger and FG the same. Okay. So let's see, now I got to apply some laws here, which I kind of already did. There's the net force being 0, which I stated explicitly. I could write an N there. That would probably be better. And then there's the net force the normal force equals the gravitational force. So I just plug that in, M times G, 80 kilograms times 10, I get 800 newtons. So this is how heavy Zach thinks he is in the elevator when it's moving at a constant speed, which is the same as when he's standing motionless on the ground. Okay. Now for the next one, the net force is not 0, so that's me applying Newton's first law again, and there's Newton's second law. I'm going to have to use that to figure out how heavy Zach thinks he is now. So Zach's brain is feeling kind of weird right now when the elevator is stopping. Maybe you've been in this position before, okay? So let's see, what am I doing? So I got to find the acceleration now because this thing is accelerating. So I need to know the acceleration before I can figure out this normal force because I know FG. I don't know what F net is. I know what M is, and I can figure out A. So I've got to work backwards. So I'm plugging things in, 0 minus 10, because it goes from 10 to 0, and then in 3 seconds, so minus 10 thirds, that's minus 3.33. And so I'm going to plug that in. I equals F net over M. The net force is the difference between the normal and the FG, and then I've got the mass there, and that's that 10 thirds. I just put that equal to the A right there, okay? And so then I came over here, and I started plugging stuff in, but I sort of did it in a wonky way. So there's my 10 thirds. I multiplied by the mass, so I've got my 10 thirds times 80 kilograms. This is actually the net force right here. And then I've got the Fn minus Fg. Okay, so the net force that Zach is needed to be pushed up with so that he stops is the 266.67 newtons. But he weighs 800 newtons, so the normal force that he feels is going to be the addition of those. So Zach's brain feels 1066.67 newtons. So Zach thinks he's a lot heavier than he normally is. And so that is how we figure out how heavy the apparent weight of Zach while the elevator is stopping. That's why you feel heavier in an elevator when it's coming to a stop. All right, so sometimes the problems are different than this. You just have to kind of work through them and think about what you know and what you don't know. We didn't do any friction examples here, so if you need to see a friction example, make sure you ask for help on one of those, okay? Thanks for watching.